All right, second half of 5.5, we started yesterday with the substitution rule. And we want to look at substitution rule today and look at it in light of definite integrals. Yesterday we were working with indefinite integrals. And so today we want to look at what happens if I do have a and b values. So let's look at the first one that we have here. We've got the integration from 0 to 4 of the square root of 2x plus 1. All right, so based on what we learned yesterday, we know that we can't integrate a quantity under a radical. So even though I'm guessing what to use for u substitution, that would probably be my guess, that I would let u be equal to 2x plus 1. So then I'm going to go through and take the derivative of u. And just a reminder of where that differential comes from, I'm going to go through and I'm going to say the derivative of u, and since that equation is in terms of x, it would be du dx. The derivative of 2x plus 1 is just 2. And then to get du by itself, I would multiply both sides by dx. And so I would get du is equal to 2 dx. So that's where we're getting that differential. So if I match it up with my problem, you'll notice that I can replace that radical and have the square root of u. But I just have dx. I don't have a 2 dx, so I need to get rid of that 2. So I'm going to go through and divide both sides by 2, so that'll give me 1/2 du is equal to dx. So again, I'm going to replace my radical with the square root of u, and I'm going to replace dx with 1/2 du. Now, here's the only thing. I've switched out all of these x's to u's, but these are still x values over here, right? So I need to indicate that to the reader by continuing to write this is what x is equal to. If I don't put those x's there, then my reader would think those are u values. All right, so then we're going to do just regular integration. I could pull that 1/2 out in front and get it out of my way. And I'm going to rewrite square root of u as u to the 1/2 so I can use my power rule. So what's the integration of u to the 1/2? Yeah, u to the 3/2 divided by 3/2, which is the same thing as multiplying by 2/3. So yeah, 2/3 u to the 3/2. I had that 1/2 out in front, so those 2's will drop each other out, and we'll have 1/3 u to the 3/2. And then we need to back substitute. So let's put the 2x plus 1 back in the place of u. So we had 1/3 u to the 3/2. So now that's 1/3 2x plus 1 to the 3/2. And that's where we stopped yesterday. That's exactly what we've done with the indefinite integrals. So now the only step that we need to add is we just need to plug in 4 and we need to plug in 0. All right, so let's go through and plug 4 in the place of x. So 2 times 4 would give us 8 plus 1 would give us 9. And then plug 0 in the place of x. So 2 times 0 plus 1 gives us 1. All right, if I'm evaluating 9 to the 3/2, like we've got right here, 9 to the 3/2 literally means the square root of 9 cubed, right? Remember, you don't have to do the 9 cubed first and get a humongous number and then try and take the square root of that. You have the option of doing the square root of 9 first and getting 3, and then cubing the 3 to get 27. So that'd be a whole lot easier. So 9 to the 3/2 is going to give us 27. So if I have 1/3 of 27, I'll get 9. 1/3 of the 27 gave us 9. And then 1 to the 3/2 is 1. 1/3 of 1 is going to be 1/3. So very similar to what we did yesterday, basically just adding on this little step of plugging in 0 and 4. The only thing about this that is kind of tedious is that I have to keep writing x equals x equals x equals all the way through here. And additionally, when I get to the end, I have to take what was a simple equation and make it more complicated again before I start trying to plug in values. And, you know, if I'm plugging in pi or square root of 3/2 or some other value like that, I don't want to have to plug it into a more complicated equation. It'd be nice if I could have plugged it into the simplified equation. So here's a second way of doing that exact same problem that I think will become our preferred method. Because one, I don't have to keep writing x equals x equals x equals x equals. That gets tedious. But two, and more importantly, I get to plug my values into that more simplified equation at the very end. Let me show you what I'm talking about. Here's that same example that we just did, exact same problem. We start off the same way over here, that what's under the radical will be u, so the differential du will be 2 dx, and we had to get dx by itself, so 1/2 du was dx. That's all the same. I have switched out all of these x's for u's. Why not switch out these x's for u's as well? I can. I can come down here and say, okay, x was equal to 4, so what is u equal to? Well, by definition, u is 2x plus 1, so all I would have to do is just say 2x plus 1, where x is 4. And so that tells me u would be 9. So when x is 4, 2 times 4 plus 1 means that u would be 9. Do the same thing with 0. If x is equal to 0, what's u? Well, I could come up here and say 2 times 0 plus 1. So 2 times 0 plus 1 is going to give me 1. So now everything is in terms of u. Not only is my integrand, that's the same integrand we had over here a second ago, not only is my integrand in terms of u, but now my a and b values are in terms of u as well, so I don't have to keep writing that x equals thing. Alright, so let's do our integration. I'll pull that 1/2 out in front and rewrite square root of u as u to the 1/2. You told me a moment ago that the integration of u to the 1/2 would give me 2/3 u to the 3/2, and we had that 1/2 out in front where the 2's cancel. So I'm left with 1/3 u to the 3/2, and here's the cool part. I do not have to back substitute. Over here, because these were x values, I had to put the 2x plus 1 back in so that I could evaluate the x's. But over here, because I've changed my x's to u's, I don't have to go back to that more complicated equation any longer. I don't have to back substitute. I can keep working with my u's. Since u is equal to 9, I can go ahead and plug that in, and since u is equal to 1, I can go ahead and plug that in. So I get rid of the tedium of writing x equals x equals x equals, and I get to use the easier equation at the end to plug my values into. So again, you'll notice we get the same answer either way, but I think we'll get to the point that we prefer this because it's a little faster and simpler. All right, let's look at another one. Example number 7. All right, example number 7, what do you want u to be?
3 minus 5x.
3 minus 5x. It's just a guess, right? So it may not work. I may have to try something different, and that's okay. So what would the differential du be?
5.
The derivative would be negative 5,
5 dx.
and then the differential, right, would be negative 5 dx. So if I look at my equation over here, I've got this taken care of. That's going to be u squared in the denominator. But all I have left up here is dx. So I got to get dx by itself over here. How do I get dx by itself? Divide by negative 5. So I'm going to divide both sides by negative 5, and I'll have negative 1/5 du is equal to dx. So, okay, I can replace that dx now. I'm good. I've replaced my entire integrand with u's, so now I want to replace my limits of integration with u's. So I'm going to come down here and say, okay, I had x equals 2, so I want to know what u is equal to, and I had x equals 1, so I want to know what u is equal to. So if u is 3 minus 5x, then I'm going to go through and plug in 2, so 3 minus 5 times 2 would be 3 minus 10, so that would be negative 7. And then we'll plug in 1 down here, so 3 minus 5 times 1 would give us negative 2. So when I come over here to rewrite this, I'm integrated from negative 2 to negative 7. Now, that looks bizarre to us, right? Because normally the lower limit of integration is on the bottom. You do not rearrange those numbers and automatically put the smaller one on the bottom and the larger one on the top. You have to put them in the corresponding position of the x value that they came from. So negative 7 came from the upper limit of integration. It came from the 2, so it has to go in the top. Negative 2 came from the lower limit of integration 1. It has to go in the bottom. Now, remember that we had a property that said that if you have the integration from a to b of a function, it's a negative of the integration from b to a of a function. Do you remember that? That you can switch your a and b values if you stick a negative out in front. So if this really bothers you, I really can't handle having the larger number on the bottom, you could switch these as long as you put a negative out in front. Okay? We're going to proceed with this as it is while we're learning this new concept. We want to try and just kind of focus on the one main thing instead of throwing in all kinds of extra theorems. But just wanted to mention that to you in case you noticed that and it bothered you. Okay, so let's come through and replace our integrand. We've already said that 3 minus 5x would be u, so we'll have u squared in the denominator. And then remember that dx was negative 1/5 du, so we'll replace dx with negative 1/5 du. I'm going to move that u up to the top with a negative exponent so that I can use my power rule. Integration of negative 2 would be...
negative u to the negative 1.
Yes, negative u to the negative 1. And I had that negative 1/5 out in front, so I could say negative 1/5 times negative 1 is positive 1/5. And you might also want to write u to the negative 1 as 1 over u to plug numbers in, whatever you want to do. I'm going to have a positive 1/5 times 1 over u, which was negative 7, and a positive 1/5 times 1 over u, which was a negative 2. And so then we can combine to get our 1/14. All right, a couple of shortcuts that we can pick up in the form of properties today. With our definite integrals, and that's on the bottom of page 360, integration of symmetric functions. When we're talking about symmetric functions, we're talking about even functions and odd functions in this particular case. Remember, we studied even in our last year. We also reviewed them back at the beginning of the year this year, but just briefly, if you have an even function, it's going to be symmetric about the y-axis. That means you can fold the graph on the y-axis and it folds on top of itself. If you don't have a graph or you don't have access to a graphing calculator for that portion of the test or quiz, there's an algebraic test for it as well, and that is when you plug a negative x into the function, you get the exact same thing that you started with. All right, for an odd function, it's symmetric about the origin. That's the one that you turn it upside down and you get the same thing upside down as you do right side up if you're looking at the graph. But again, if you can't graph it, the algebraic test is you plug in a negative x and you get the opposite of what you started with. So those were the definitions that we worked with last year and the beginning of this year. So here is the property that's going to be helpful for us. If you have an even function and you are integrating from negative a to a, so that would be like from negative 3 to positive 3 or negative 5 to positive 5. Those numbers have to be opposites of each other. Then that function would be the same thing as double the integration from 0 to a, basically just the positive side of it. Look at the picture and you can understand it better. If this function is even and it's being integrated from negative 5 to positive 5, whatever this area is over here, maybe this area is 3, this is going to be the same area over here. It's going to be 3 as well. So instead of having to find the integration from negative a to a, maybe you would prefer not to work with negative values. You can just find the area under the curve of this positive piece, the integration from 0 to a, and then double it. So that's what this says down here. Find the integration of the positive side of it from 0 to a and just double it. The second one is even better. If your function is odd and you're integrating opposite upper and lower limits of integration, your answer will be 0. Because look at your function. If it's odd, you're going to have a part of it above the axis and a part of it below the axis, and they're going to be symmetric to each other. So if you get a positive 5 over here, you're going to get a negative 5 over here. They're going to cancel each other out and give you an area under the curve of 0. So let's look at a couple of examples. Example number 8, the way to spot these is when A and B are opposites of each other. So you see that in example 8 and 9. There's no need to even check for symmetry unless that's the case. Okay, so I look at example number 8 and I've got x to the 6 plus 1. And I want to see, is there any chance that's an even or an odd function? I could graph it if I have that opportunity, but if not, then I could do the algebraic test where I put a negative x in the place of x in the function. So if I put a negative x in the place of x in that function, I get the exact same thing that I started with. So what is this? Even, odd, neither? Even. This one's even, right. So if it's even, I absolutely could go ahead and integrate this exactly as it is. I don't have to use this symmetry shortcut. But I could go through and say that area under the curve would be the same thing as if I just found the positive piece from 0 to 2 on the positive side of the x-axis, and then I doubled it. So again, you can go either way with this. Now, I know that we're good with integration, so I'm not going to show all the work for the integration of x to the 6 plus 1 from 0 to 2. That gives us 142 over 7, and then I would just double that to get the area from negative 2 to 2. If you did the area from negative 2 to 2, you did the original integral, you would also get 284 over 7. So it doesn't matter which way you do it. All right, look at the next one. For the next one, I noticed these opposite values for my upper and lower limits, and so I checked to see, hey, is there any chance that this is symmetric? It's even or odd. So again, I'm going to do my algebraic test where I put a negative x in the place of x in the function. Now, this is going to require us to remember a formula from last year about this time. It's actually something we're doing in pre-cal right now, and that is tangent of negative x. Tangent of negative x is negative tangent x. So if tangent negative x is negative tangent x, I'm going to have that in my numerator. In my denominator, negative x squared and negative x to the fourth both go back to being positive x squared and positive x to the fourth. So if I factor a negative 1 out of that thing, you can see I get the exact opposite of the function that I started with. When I get the opposite of what I started with, what does that make this? Odd. So if this is an odd function, my answer is automatically 0. So that's a really fun shortcut.